Welcome everyone to Casio's educational webinars. Tonight you're listening to a fundamental approach to connecting families of functions using transformations, part 1. Your presenter tonight is Tom Beattini, and I am the panelist tonight. My name is Nevels. We are both members of CTAC, which stands for Casio Teachers Advisory Council. Tom has over 30 years of experience in education. His undergrad degree is in secondary math education from the University of Vermont. His master's is from New Jersey City University. Tom has been working with graphing calculators since 1990. He's presented workshops that focus on implementing the graphing calculator in the classroom at conferences on the state and national levels. Effective implementation of graphing calculators at all levels can unlock some of the mysteries of mathematics through the power of visualization. And tonight you'll get to see Tom do some of this magic. So without further ado, I present to you Tom Beattini.
Thank you, Nevels. Welcome everybody to our webinar this evening, a fundamental approach to connecting families of functions using transformations. And transformations are one of the important content areas of the Common Core state standards. And what I have done here is I have listed some of them that we're going to be addressing this evening, like the standards for mathematical practice that you can see, such as making sense of the problem and persevering in solving them, reasoning abstractly and quantitatively, looking for and making use of structure. And after that, I have some of the standards that are embedded in the algebra functions and number strands, such as interpreting functions that arise in applications in terms of context, analyzing functions using different representations, and building new functions from existing functions. These are all important aspects of gaining an understanding of what functions are about at the secondary level. Before I continue, one of the things I want to remember to tell everybody is that if you would like copies of the documents that I am going to be referencing, some of which I am going to be showing, please email me and I will send them to you. Let's see here. All right, so now we are at our graphing calculator, and we are going to be talking about families of functions. The basic family that we are going to be talking about is the linear family. This is the one that students start off working with in Algebra 1. And what we want to do on our calculator right now, and if you have a calculator handy, you can follow along, is we are going to enter in y1 the function y equals x. So I don't want to do that. Let's see, let me get my, okay, here we go, y equals x. And we want to store that. That is, we are going to call this for the next bit of time our parent function. The next thing we want to do is we want to select the viewing window, so we want to do Shift F3 for our viewing window, and for our purposes here, we want to have the initial window. So since we have our window set, we want to exit and then draw our basic function by pressing F6. So here is our function y equals x. Now, one of the things that we can do on the Casio Prism is that if we use two of the hotkeys that I'm pointing at here, the plus sign and the minus sign, if we by pressing the plus sign, we can zoom in on our graph. And then by pressing the minus sign, we can zoom out on our graph based on our zoom factors. We can also manipulate the screen by using the arrow wheel by moving it up and down, and to the right and to the left. So if we press trace here, we could identify some of the values that we have along the line y equals x, so we can cursor over to 1, 1. But right now we're not as interested in tracing as we are as in manipulating this equation. So what we want to do at this time is in y2 store the function y equals ax. So we're going to press the alpha key to activate the a, and then the x. Press execute to store it. And what we want to do now is we want to press F5 for modify. So what you see on the graph is that the blue graph is y equals x that we had before, and the red one is y equals ax. Now, in the bottom right-hand corner of the screen, the left-hand corner of the screen, we see an arrow on pointing at a, and we see a step value. This allows us to manipulate our equation. So what I can do, I can press execute and automatically enter a value of a, and then what I'm going to do for argument's sake is enter 1. And by doing that, we have the blue line that we had before, y equals x, is now y equals ax, y equals 1 times x. And the yellow line we have here is the trace of our old graph. So that is what you will always see whenever you use the modify feature of the calculator. You will see a yellow line, which is the trace of what the graph was, and then the new one. So now what we can do is, by pressing the right and left arrow of the calculator, we can increase by a value of 1 the coefficient of x. So if I press the right arrow, you notice now the value of a is 2. And now we have the value of a is 3. And if you take a look at this particular red function that we have stored in y2, it has the same x-intercept and y-intercept, and that's going to be the origin. Now, if we decreased the values of a, I'm sorry, I hit the left arrow. And made a 0, we're going to have a horizontal line because the slope of any horizontal line is going to be 0. Now, if I press left arrow again, we are in the realm of lines with a negative slope, or as I tell the students in my classes, we have a downhill line. So when we have a line that passes through the second and fourth quadrants like we have here, and the origin, we have a downhill line. And when we have a line that passes through the origin as well as the first and third quadrants, it is an uphill line. So the value of a in this particular instance is not going to change the x-intercept or the y-intercept because it's always going to be the origin. Now, when we have the modify feature on this calculator, if we want to go back, what we can do to where we were before, if we press exit 1 time, we are now on a screen that allows us to trace. And we're using the previously stored value of a. So in this case, when we trace, we are on the line y equals 1x because we had a stored as 1. And now we can move along it if we so choose. If we press exit a second time, we go back to the equation editor. So does anybody have any questions so far as to how we are modifying our line, and also how we use the hotkeys on the calculator?
Seems like we have no questions yet, Tom.
Okay. All right. So what we are going to do now is we are going to manipulate this second equation. We are going to introduce a second variable. And we're going to have y equals ax, and I'm going to add a b. So like we had before, we have a, which represents the slope of the line. And what we want to do now is try to figure out exactly how do the values of a and b affect what the graph is going to look like. So let's press execute to store the function, and then we are going to press F5 for modify. And if you notice, we now have in the lower left-hand corner of the screen two variables that are displayed, A and B. So what I'm going to do now is just give us a starting point. I am going to make A 0. So we have a line that is, in essence, y equals 0. And what we can do at this stage of the game is, since we have two different variables in the step, we can manipulate both of them. So if I press the right arrow now, I'm going to be changing the slope of the line, and it still passes through the origin. What I can do now is, if I down arrow, to B, what I can do is I can change the equation, and notice what happens. The line moved. We start off with our parent function as the blue line. The previous line we had before was the yellow one here, y equals 2x, and now we have the red line, and the line is jumped up from the origin 1 unit. If I press the right arrow again, we have the red line jumping up to this point here, 0, 2. So what we can do is we can use the right and left arrow keys or input a value to explore what happens to the function if we manipulate the value of b. So if I was going to press execute and type in a value of b like -1, we've got the red line here, which is our new line. We have the yellow line, which is the old one, and this red line, the y-intercept is changed. It is now 3 units below what it was before. So the thing we want to ask ourselves at this point is, how does the value of b affect where the line is going to cross the y-axis? So if we take the value of b and let's say make it -1.5, we're going to move the line down just a little bit. If we made it +1, it's going to jump up above the origin. So what we can do here is we can see that from the way the graph is jumped, the value of A is going to affect the slope or the tilt of the line. The value of B is going to change where the line crosses the y-axis. So this leads us to an important question. If we take a look here at letter D, if we want to describe and compare the graphs of y equals 2x and y equals 2x plus 1.5, notice the values of A here are the same. The values of B are different. So these two lines, slide things over a bit here. This, in a way, kind of reflects what is going on here with the yellow line and the red line. Those two lines, because the values of A are the same, are going to be parallel. And they have different y-intercepts. If we were going to take a look and compare the two lines, y equals -1.5x, I'm sorry, y equals 1.5x and y equals -2x minus 1, what we can do is we can type it, we can change our value of b. Let's enter for the first function. So we can make b -1. What did I do wrong here? Okay, there we go. And I'm going to scroll up and make a equal to 1.5. So that's the first line that we have, and the second line is going to be -2x minus 1. So if we have our red line here, y equals 1.5x minus 1, and now what I'm going to do is I'm going to make this line well, I think what I'm going to do, well, let's see what happens here. Make that -2 and make the value of b -1. So what we would have then is we'd have, well, I think I goofed. What I should have done is I should have exited and I should have graphed both of these functions. So let me exit twice, and what I'm going to do is I'm going to type in 1.5x minus 1 in y1, and then I can delete this from y2, and then I'm going to type in -2x plus 1. I'm sorry, -2x minus 1. Then if we draw them, well, we have two lines with different slopes. We have an uphill line and a downhill line, but they share the same y-intercept. So what we can conclude here is that the value of A is always going to manipulate the slope of our line, and the value of B is always going to show us where the line crosses the y-axis. Now, let's exit this, and this is the second style of function we could have in what I call the linear family. So what we are going to do now is I'm going to clear these two functions out, and go back to y equals x. And now what I'm going to do in y2, I'm going to store a different function. You might see some resemblance to the one we looked at earlier. We're going to do alpha a parentheses x minus alpha h plus alpha k. And we execute the store, and now we are going to modify this. So now you see in the lower left-hand corner 3 variables, and we see our blue graph, which is the parent function. And what we want to do now is we just, for argument's sake, I want to make all these values 0. So our line covers up the x-axis and passes through the origin. Now, we've looked at what happens when we manipulate the value of a. So this gives us an opportunity to see what happens when we manipulate the values of h and k. All right, so what we're going to do is we are going to make a equal to 1. And if you notice, we have the yellow line, which is what it was, the trace of what our line was before, and we have the red line, which is y equals 1 times x minus 0. Well, x minus 0 is x, and we add 0 to that, we still get just plain old x. So we got the equation we had before. And what we can do at this stage of the game is we can manipulate the value of h. So if we manipulate the value of h and enter something in like 2, the graph is shifted to the right. If we press the right arrow, we can get it to shift to the right again, because there is our trace from what we had before. And if we shift it to the right one more time, we have h equal to 4. Now, one of the things that we can notice here is that the value of h, the line passes through the point 4, 0. The value of h is 4, the value of k is 0. So that might tell us something in terms of where or a location on the coordinate plane that our line is going to pass through. So if we decided to type in another value of h like -1, okay, we have our yellow trace from before here. Now the graph is over to the right of the origin, so it's now 1 unit to the left. So the value of h in this particular instance tells us something about where our line is going to be in relation to the origin. When it was positive, it was to the right. It was to the right of our blue line. When it's negative, if I press the left arrow again, it's going to move a little bit more to the left. When h is negative, it's going to be to the left of the origin, to the left of our parent function. Now, let's manipulate the value of k. So if I changed the value of k from 0 to 1, we have our yellow trace right here, and the line, we had the line passing through the point -2, 0. Now it's moved up 1 unit. If I do it again, our previous line is now moved up 2 units. So it seems we have k is equal to 2. K tells us something about how the line is going to move vertically. So k is going to be the variable that affects how our parent function, our parent line, moves up and down. If we typed in -2, it should shift 2 units below the x-axis. So here we have our point, -2, -2, which correspond to our values of h. So one of the things that we can conclude about our line in this particular case, and notice a is equal to 1, so our graph of our line is being traced right over our parent function, is that we have a situation where the value of h and the value of k are always going to represent the ordered pair of a point on our line. And this leads us to a discussion of domain and range. So when we have a line like we do here, we are going to have a domain which is going to be all real numbers, because whenever we put in a real number value of x, we're going to get a real number value of y. And in terms of our range, because we have inputs that are going to be real numbers, we're going to get a output, a y value, that will also be a real number. But let's verify something that's going to connect back to what we discussed earlier when we were talking about the function y equals ax plus b. So what we are going to do now is we're going to manipulate some values here. And I'm going to make a equal to -0.5. Okay, and we are going to make h equal to 4. And we are going to make k equal to -1. All right, so what we want to take a look at this stage of the game is, as you can see, we have the point 4, -1 is on our graph. But this might represent the equation of another line that we talked about before. We were thinking in terms of representing a line with a value of a and a value of b, where b represented the y-intercept. So let's take a look at the steps here of going through the process of simplifying this expression that we had before. We're going to substitute in our values of a, h, and k. So we're going to plug and chug. And then we are going to use the distributive property, and then we are going to combine like terms. So when we do that, we get the equation y equals -0.5x plus 1. So let's leave this screen. And press exit twice. And in y3, what we are going to do is type in the equation y equals -0.5x plus 1. And press execute. And now let's press F6 to graph it. So we had the red line that was graphed before, and we had our values of h and k, and now we had the green line, which traced over it. So any line can be represented in terms of three variables, a, h, and k, but when it becomes simplified, we go back to what we had before. Press exit. We have something of the form ax plus b, where in this case, the value of a is negative 0.5, and the value of b is going to be 1. Does anybody have any questions or comments at this stage of the game before we continue, because we're going to be spending a lot of time talking about h and k?
Tom, it doesn't seem like we have any questions at this point.
Okay, all right. So now let's talk about some more interesting functions. All right, we are going to clear these out. All right, let me delete these. And now we are going to talk about one of my favorite functions, because I think this is the one that gives everybody, if students can understand the absolute value function and how it behaves, this is their ticket to understanding how functions behave when we're talking about moving them around and transforming them. And the whole goal, as I said earlier, in our title is a fundamental approach to families of functions using transformations. We want to try and make this as interesting for the students as we possibly can, and the graphing calculator is a great way to do it, especially when they get to examine on their own and investigate exactly how functions are going to behave. So we have to find the absolute value function here. So that's going to be under option, F5 for numeric, then F1, and I can store an X. I'm going to store the function by pressing execute, and now I'm going to press draw. And now it looks a lot different than something we had earlier. We got a V shape. And what we want to pay attention to is the values of X when X is going to be less than 0 here, and when X is greater than 0. So one of the things we want to think about is some students call this function the rebound function. And you know, I like to hold students' feet to the fire and say, well, why do you call it the rebound function? Well, you know, it comes down, the line it comes down, and then it bounces off the origin. And I would accept that as a reasonable argument for why a student might call this the rebound function. So now if we decided to trace on this, you can see here, if I go a little bit to the left and then start increasing, the values of X get smaller as we take the absolute value. And then when we get to the origin, they start increasing. I forgot, I should go into my setup and turn off my derivative. I had my derivative on for a while. I don't mean to confuse anybody. So we're going to do an F2 to turn it off, and then draw again. So now when we trace, there's no more derivative. So the question we want to ask ourselves here is what are the domain and range when we look at the absolute value function? Well, in this particular case, the domain is going to be all real numbers, but the range, all the values that we looked at before and we traced, are going to be positive. So the domain is going to be all real numbers, and the range is going to be all values of y that are greater than or equal to 0. this is our basic parent absolute value function. So if we press exit and then we go into Y2, what we are going to do now is we are going to store in Y2 alpha A times the absolute value of x. Now let me delete that. I forgot to do my numeric, my absolute value. And then press execute. So the blue graph is going to be our parent graph, and now what we want to do is we want to modify our red graph. Okay, so we are in the modify feature, and notice we have a negative value of A. So let's make this a positive 1. And the red graph looks like the parent function we had before. So if we increase the values of A, make A 2, make A 3, notice the V starts getting narrower. So we've got positive values of A in this particular instance, and what's going to happen when we have positive values of A, we have the absolute value function is the union of two lines. Here in the first quadrant, we're going to have a line with a slope of 3. Notice the value of A here is 3. And in the second quadrant here, we have this part of the graph, this piece, is going to have a slope of negative 3. So when we're talking about the two pieces of an absolute value function, each of them are the slopes of each piece is going to be the opposite of the other. Now, let's see what happens if we're increasing the value of A, it gets narrower than our parent function. Let's see what happens if we made it a fraction like 0.5. All right, so now here is our modified absolute value function, and it's wider. So if I were to make it negative 0.25 or negative 1/4, it gets wider still. So what's happening is the value of A is going to do something to the way the function opens up. How we can make the parent function narrower, or how we can make it wider. So what we can do then is think in terms of, as the values of A increase, we get a narrower graph, a narrower function. As the values of A decrease and get closer to 0, we're going to have a much wider function. Now, let's see what would happen if A was equal to 0. So if you type in 0, very interesting, we get a horizontal line. So if the value of A is 0, we're going to be multiplying any value of x times 0. So this means y equals 0. Some students would argue that this is not the equation of an absolute value graph. Well, we could have long discussions with our students and with our colleagues about this if we so chose. But if I was going to use the left arrow now I've got a graph of an absolute value function that is below the x-axis. And notice the sign of A is 1. The sign of our parent graph, the blue one, the value of A is positive 1. So is there a connection between these two graphs? Well, when we change the sign of an absolute value graph, the value of A in an absolute value graph, it is going to be the reflection image of an absolute value graph where the value of A is its opposite. So opposite values of A are going to give us symmetry on the coordinate plane. And what's going to end up happening in a situation like this is we're going to have a graph that opens down as opposed to a graph that opens up. So as the value of A is positive, we got a graph that opens up. If the value of A is negative, the graph opens down. So if we increase, I'm going to change my wording a little bit here. If we take a look at the absolute value of A, okay, thinking in terms of the absolute value of A in terms of an absolute value function, and don't worry at all about its sign, then what's going to happen is we're always going to get a graph as all right, here the absolute value of A would be 2. We're always going to get a graph that is going to become narrower and narrower. So let's do what we did before, and let's exit this. And now what we are going to do is we are going to manipulate this second equation, and I am going to do what we did before with our line. I'm going to put in a minus h and add a k. And then press execute. All right, and let's modify this. Now notice we have 3 variables that appear here in the lower left-hand corner, but what we want to do to get started here is we want to start off with A being equal. Let's make A equal to 1, and we're going to make H equal to 0 and K equal to 0. So if you notice, the red graph that we have here, from what we looked at before at the line, H and K represented the coordinates of a point on a line, and here for the absolute value graph, the value of H and K represent the coordinates of the origin of the point of our V. So now if we think in terms of what we did before at the value of A was making the graph narrower or wider. Let's see what happens if we manipulate the value of H. We increased H by 1. The graph moved. Every time we increase the value of H, the graph is moving to the right. So in this case, H is 3. We have a point on the graph that's going to be 3, 0. So the value of H does something to the parent graph. Let's see what happens if we make H negative. Let's type in a -1. Oh, now if A is -1, the value of H moves the graph to the left. So if H is negative, the graph is going to shift to the left. Let's let me delete that, and let's make H -3. All right, so this tells us, based on what we've looked at here, the value of H is going to shift our parent graph to the left or to the right. Now, let's see what happens with K. Right now we're at this point. Let's make K +1. And we have our yellow trace right here. And what we've just done is we have moved the graph that we had up 1 unit. And if we press execute again to increase the value of K to 2, it's now moved up 2 units. So in this particular instance, if I wanted to type in a -3, for example, right? We have the point right here, -3, 3. Notice the values of H and K are -3, 3. So this tells us something about what the graph of a function is going to look like, of an absolute value function is going to look like, if we know the values of H and K. So here we can say to ourselves, all right, each branch is going to have a slope of 1. Well, we're going to have the right branch is going to have a slope of 1. The left branch is going to have a slope of -1 because we're looking at our values of a. And the vertex of our absolute value function is going to be -3, 3. So this allows us to manipulate the function. And one of the things we can also do is take a look and see at the domain and range. Now, for our parent function before, we had the blue graph, and the other piece of the blue graph is overlapped by the red one here. In fact, let me just shift this a little bit so that this way it gets out of the way. Let's make this let's change that to a -2 so you can see the parent graph. Now, if you notice before, we had the domain was all real numbers and the range was all values that were positive, all values that were above the vertex. Here, for our red graph, we are going to have a domain of all real numbers, but notice where the low point is. The low point is at the point the vertex is at -3, 2. And since k represents the y coordinate, that's going to tell us the range for our function is going to be all values of y greater than or equal to 2. Now, if we were going to change a couple things here, let's do this. Let's change this to a to -2. What happens to our domain and range? Well, now, since a is negative, our graph opens down, and we have a maximum point. The domain for our absolute value function is always going to be all real numbers, but since the maximum point of our graph here, all the y values are below -2, we would say that our range is all y values less than or equal to -2. So with the absolute value function, students, if they can understand what happens with the sign of A, opens up or opens down, determines how the graph opens up or opens down, the value of h is going to shift the graph to the right or to the left, the value of k is going to shift the graph up or down. Those are the fundamental concepts that students need to understand in order to be successful with working with other families of functions. Because we think in terms of the value of a as making our parent graph wider or narrower, so we're doing a stretch or a shrink, and the values of h and k, well, they help the function dance, or as we say mathematically, translate the function. So the value of h translates the function horizontally, the value of k translates the function vertically. Now, one of the things I would, it's not this document, let's close that out. If we take a look at a graph here, one of the things we might do with our students after they spend some time exploring this is ask them, taking a look at the graph that you see here on the screen on the left, is what is the equation of this graph? Well, the first thing to do is to identify the vertex. So the vertex here is 3, -2. So that tells us we're going to have some value of a times the absolute value of x minus 3 plus 2. Now to determine the value of a, we've got to take a look at the slope of the branches. So here we have the slope of the right branch. We can go up 1, 2 to the right. So that tells us a might be a half. Well, let's see. If we said before that the value of a for an absolute value function for both branches was going to be opposites. So if we go up 1 and then 2 to the left, that gives us a slope of -1/2. So for this function, then what we have is we've got y is going to be equal to -1/2 times the absolute value of x minus 3 inside the absolute value signs, and then a -2 outside. So this, by sharing graphs with students like this, you can give them an opportunity to test their knowledge of what is h, what is k, And what does the value of A do? So, that being said, let's make things a little bit more interesting. And let's press exit 2 times. And what we are going to do is delete our 2 functions. And now we're going to talk about another family. And this is a family that's very fundamental to a fundamental family when it comes to the study of polynomials. And it can be represented in a number of ways. We're going to take a look at one particular representation tonight, and that is vertex form of the quadratic family. Or, as I tell my students, the parabola guys. So, we have a parabola guy here, and he looks a little bit like the absolute value function, but he's curved. Now, one of the things we can look at here is we can think in terms of some of the properties of the parabola. Well, the parabola has a lot of the same properties of the absolute value. Okay, we have a domain here that's going to be all real numbers. We're going to have a range that's all y values greater than or equal to 0. We've got a vertex here at 0, 0. But now we want to manipulate this parabola guy. So what we are going to do in y2 is we're going to type in alpha a times x squared. Press execute to store it. And now we are going to press F5 for modify. Oh, wait a second, hold it. We're using the previous value of a that we had before. We were using the absolute value functions. Notice what happened here. The value of a is negative, and our parabola guy, he opens down. Now, let me make this. Let's manipulate the value of a and make this -1. All right. So notice that we have 2 graphs, y equals -1x squared, and y equals, in red, y equals +1x squared here in blue. Do you think there is a connection between them? Well, let's think of what we said before about absolute value graphs. We had 2 absolute value graphs, and the values of a were opposites. One was the reflection of the other over the x-axis. So there is a geometric component here as well. So this begs the question, if we increase the value of a here, what happens? Oh, we got a line. Now, again, this goes back to what we were doing before with absolute value graphs. Some people might say that this horizontal line here covering the x-axis does not represent an absolute value function, or in this case, a quadratic function, a parabola. Well, if we increase by 1, notice we have our value of a is 1, and we're back to our parent function, y equals x squared. So now, let's increase the value of a. Notice what is happening to our graph. The graph is getting narrower. Something very similar is happening here that happened to absolute value graphs. So as we keep increasing the value of a, we now have what looks like a, for those people who like different beverages, a champagne flute effect when a increases. But if I take the value of a, let's say type in 0.5 or half, we have the yellow one that we had here before, but now it's this here in red. So it's wider than our parent graph. So if I made this 0.25, it's going to be wider still. So when we take the value of a and make it smaller, make it approach 0, in this particular instance, what's happening is we're not going to have a champagne flute effect, we're going to have more of a soup bowl effect. If I made it 0.1, I could make it wider still. So there we have an absolute value graph where A is equal to 0.1. So when we look at the value of A with a quadratic function has the same effect on the function that it does with absolute value. The value of A will make the function wider or narrower. The sign of A, okay, let's make this negative 0.1. Let's see what happens. The sign of A is going to tell us whether the graph opens up or opens down. So when A is negative, we have a graph that opens down. Our domain is going to be all real numbers. But now our range is going to be all y values that are going to be less than or equal to 0. So we've made a connection here between absolute value functions and quadratic functions. Our parabola guys, the value of A does the same thing in each type of function. So let's press exit 2 times and go back and manipulate our y2 a little bit more. And let me delete here, and in parentheses I'm going to put in x minus alpha h squared plus alpha k. Now this looks a little bit like what we had before with the absolute value graph. So if I press execute to store it and then press F5 for modify, well, notice the value of A that we had before is negative 0.1. Let me change these values here so we have a basis for starting. So now we have our graph over our parent function, and we've taken a look at what happens when we manipulate the value of A. Now, let's manipulate the value of H. The graph moves to the right. So with a quadratic function, like with an absolute value function, the value of H has the same effect. We can always manipulate a graph when we have a general equation, x minus some number squared. That number is going to tell us, that number we are subtracting is going to tell us how much we are moving to the right or to the left. So if I made this a negative 2, h negative 2, right, this tells us that we've moved, because h is negative, we are moving 2 units to the left, even though it may appear to be different when we simplify the signs in our parentheses. So the value of h always has the effect of moving a graph to the right or to the left. Now, do you think what the same thing is going to happen if we manipulate the value of k? Notice we have our vertex here, negative 2, 0. So if I was going to change k to positive 1, notice the graph is going to shift up 1 unit. So again, we have some of the same properties exhibited here with the quadratic function that we do with the absolute value function. In terms of the vertex, which tells us something about our domain and our range, we're going to have a domain of all real numbers. In this case, since our low point of our graph is going to be at negative 1, where y is equal to negative 1, the y coordinate of that point, y greater than or equal to negative 1 is going to represent our range. If we made A negative 2, our range would be y is less than negative 1 because the graph opens down. So the sign of A tells us whether the graph opens up or opens down, whether or not we have in this case for the red function, a maximum point, a high point in the graph, or in the case of what we had before, the yellow graph, a minimum point. So maximum points and minimum points are important points when we are thinking in terms of functions that bend. And we can talk more about that in a future webinar when we entertain ideas about third degree, fourth degree, fifth degree functions. So if we are going to look at, well, we were about out of time. Let's see. All right. We're about out of time, everybody. So before we close for this evening, are there any questions or comments related to what we've discussed about linear functions, absolute value functions, and quadratic functions in terms of manipulating them and using the variables a, h, and k?
Tom, they seem to be all squared away.
Okay. Well, everybody, thank you very much for attending our webinar this evening. We hope you come back to a future Casio webinar, and have a good evening. Thank you very much.